All right, in this video, we're going to go over another Chem Phys passage. You can actually find over 3,500 MCAT practice questions on our MCAT question bank, but today we're just going to cover 6. So I want to start this tutorial by pointing out that every single MCAT passage except cars is experimental. So oftentimes at the bottom of a passage, they'll actually cite what journal the experiment came from and who the researchers were. And as a result, most passages have figures, so you'll probably have to consult the figures quite a bit to answer the questions. And each passage will start with an introduction before going on to explain what the researchers did in the experiment. So in the first paragraph, you want to try to ascertain what kind of MCAT-ish topic we're dealing with here. So let's go ahead and take a look at the first paragraph of the passage that we'll be dealing with today and see if we can ascertain what those are. All right, so it reads, efficient operation of microelectronic devices heavily depends on temperature management, namely the dissipation of waste heat away from the electronic device. A heat pipe is a device that transfers heat away from its heat source by directing thermal energy into vaporizing a working fluid. The hot vapor then moves into a condensing section of the pipe, where it is condensed into a liquid and pumped back to the evaporating section, thus completing the thermodynamic cycle. So from this, we can gather that they're talking about heat transfer between a pipe and a liquid and how the liquid vaporizes and condenses in a thermodynamic cycle. So when reading intro paragraphs, the simplest way to determine what they're talking about is to look at the first and last sentences. You might not get all of the information that you need right off the bat, but it's really going to help you narrow your focus from the get-go. So here the first sentence discusses dissipation of waste heat, and then the last says they just completed a thermodynamic cycle. So ultimately, it's about heat transfer. And if I'm underlining MCAT buzzwords, keywords that I really want to pay attention to, then I'm definitely going to underline vaporizing and condensing, since they deal with heat transfer and phase changes. So searching for buzzwords on the MCAT is always going to be pretty important because it really allows you to identify the general scientific principle that the test maker is trying to examine you for. And that can make you more efficient and more accurate in your answers. Because really the MCAT isn't so much a trivia recall test as it is about how you can use the fundamentals that you should have already learned in a new setting. And buzzwords really help set those subconscious reminders of what formulas, processes, or principles you should be running through mentally and trying to recall. So for instance, if you see a word like vaporize, you should immediately think phase changes, heat transfer. And then that can help you narrow down which equation or concept you're going to need to apply for this passage. This method really does help save a lot of time. It helps you decrease your second guessing, and it helps you stay focused on just what's most important in each paragraph. So if you're looking for more info on MCAT buzzwords, you can definitely check out our comprehensive list of high-yield key terms that are listed at the bottom of every content unit in our MCAT Premium Content Hub. All right, so let's go ahead and move on to the second paragraph. It reads, a typical flat heat pipe is composed of a container, a working fluid, and a wick structure. An innovative wick structure produced using 3D printing technology utilizes microgrooves to maximize the vaporization of the working fluid. A prototype of the newly designed heat pipe was produced from aluminum. The final dimensions of the prototype measured 100 millimeters in length, 10 millimeters in width, and 4 millimeters in height. So the experimenters are using a heat pipe, and based on what we read in the first paragraph, we can reasonably infer that they're going to use it to assess phase changes or a thermodynamic cycle. And then in the second sentence, we have the word vaporization, which is one of those key terms that we identified. And we may or may not use those numbers in the last sentence when we get to the questions. So for now, we'll just highlight them so that they're easy to find in case we do need them. And by the way, if you're not understanding everything that the passage is describing, that really is okay. The MCAT will throw at you a lot of information that is unnecessary. And then once you get to questions, they'll ask for more basic info generally. And that's why it's really important to orient yourself by looking for those key terms and the main idea or the object of the passage, which of course in this case is the heat pipe. So to quickly review paragraph 2, it says that the heat pipe is made with 3D printing technology that enhances vaporization. And then the other 2 sentences describe the physical composition of the heat pipe. So on to paragraph 3. To evaluate the heat transfer performance of the pipe, thermocouples were placed along the length of the pipe and used to evaluate the temperature of the pipe during operation. The experimental setup and results are shown in figure 1. Okay, figure 1 shows us 2 things, a heat conduction measurement setup, and then the results of the experiment in the form of a graph of temperature changes over time for each position in the heat conduction measurement setup. So we've got this nice figure here. And just to recap, the heat conduction measurement setup is used to study heat transfer, which is a really critical topic on the MCAT, by determining how temperature changes are distributed along a material when the material is heated at one end and cooled at the other. So one side is heated by a direct current, a DC power supply, and then the other side is cooled by a cooling bath. And that results in a temperature gradient. So thermocouples, T1 through T5 here, are distributed along the material to record temperatures at different positions, and the recording data are gathered by the data acquisition system and then transferred to a computer for analysis. So the experiment here shows the fundamentals of thermal conduction, the process by which heat moves from a hotter area to a cooler one, which has implications for critical MCAT themes like temperature gradients, energy, and work, and the significance of conductors in carrying thermal energy. So in figure 1, the most important thing is the caption and then the X and Y axes, because they're assessing the temperature evolution of the heat pipe at a power of 2 watts. That's another number to underline. At different positions along the heat pipe. So in practice, we will want to determine what the graph is telling us and what conclusions we can draw from it. And we're reviewing these graphs pretty slowly right now, just in order to learn how to analyze them. But when you get to the actual test, you want to be able to just do this on autopilot, kind of skim through the graph and then come back to it later. So for example, when we're analyzing the results of thermocoupler T3 going from time of 0 to 10 minutes, the temperature change is about 10 degrees Celsius. So this is just showing that based on the various positions of the thermocouplers, there are varying degrees of temperature change over a period of 10 minutes. All right, let's move on to paragraph 4. It reads, acetone was selected as the working fluid of choice. Filling the pipe with a 10% fluid filling ratio provided optimal heat transfer performance with low thermal resistance. Several thermodynamic properties of acetone are listed in figure 2. And figure 2 shows us all of these thermodynamic values of acetone. And this is something that we don't really need to worry about until a question asks us about thermodynamic equations involving acetone. And since this paragraph actually explicitly tells us that acetone was selected as the working fluid of choice, anywhere that the passage says the heat pipe transfers heat and then directs that into a working fluid and vaporizes that fluid, the fluid that it can be assumed to be referring to is acetone. And this is something that you see in a lot of this type of passage. Research passages usually start with a more general concept of an experiment, and then they get more and more specific as you read on. So it's important to take note of those specific details as they begin to reveal them to you. Okay, so now that we've read through the entire passage, let's go ahead and jump into the questions. Question 1 asks, the specific heat capacity of aluminum is 0.90 joules per kilogram Kelvin. Assume the heat pipe has a mass of 10 grams. What is the expected increase in temperature of the cooling bath around T2? The mass of the cooling bath is 20 grams with a specific heat of 4.184 joules per kilogram Kelvin. So what's going on here is heat transfer. And we know that because, for one thing, they're talking about the increase in temperature of something that is not aluminum. So we have two different subject matters. We have the cooling bath, and then we have the heat pipe, which is composed of aluminum. So in this question, the heat pipe and the cooling bath can be considered a closed system in which no heat is lost to the outside. So we can use the principle of energy conservation, which is a key MCAT topic, by the way. And because energy is conserved, the heat lost by the pipe should be equal to the heat gained by the cooling bath. So the two heat equations are going to be set equal to each other. And that means Q pipe equals Q bath, because both equations use the general equation for heat transfer, which is Q equals MC delta T. So by equating these expressions and then solving for the temperature change, or delta T, of the bath, then we can find out how much the bath's temperature increases as it absorbs heat from the cooling pipe. And this illustrates a really important use of the specific heat formula in calorimetry, which shows up pretty frequently on the MCAT in the form of questions about heat progression and thermodynamics. Okay, so anytime we're faced with a math problem on the MCAT, we want to determine what we know and what we don't know. So what do we know here? We know that the mass of the pipe is 10 grams, and we know that the heat capacity is 0.90 Kelvin, and we know that the temperature should be in kelvins because of the units. So in this case, because our answer options are in Celsius, we will have to do a conversion of units in order to find our correct answer. And in case you need a refresher, those conversions are Kelvin equals degrees Celsius plus 273.15, and degrees Celsius equals Kelvin minus 273.15. But one thing to note for this particular problem is that since you're calculating heat transfer using Q equals MC delta T, you're actually solving for a change in temperature, not the absolute temperature. So you don't actually have to convert to be in terms of Kelvin or Celsius. A change in temperature of 1 degree Celsius is going to be the same as a change in temperature of 1 Kelvin because they increase in the exact same intervals. So in terms of numerical value, delta T is the same in Celsius and in Kelvin. And this is because it's the difference in temperatures that's important when you're making a heat transfer calculation. It amounts to exactly the same thing, whether it's delta T, whether the delta T is expressed in Celsius or in Kelvin. Now, if we're converting to Fahrenheit, for example, which is pretty rare on the MCAT, you would have to convert back. But if you're dealing with a change of temperature, then you don't have to convert between Kelvin and Celsius because you're going to get the exact same answer. All right, looking back at the question, if we're going to do this calculation, we need to know the temperature. It's actually not mentioned in the question, but what the question did mention is that the temperature change is going to be around T2. So that's our cue to go back to figure 1 and find the change in temperature of the pipe. So looking at that, T2 is magenta from 0 to 10 minutes. It's about 5 degrees Celsius. And then what about the bath? We know the bath is 20 grams, and then they gave us the heat capacity. So since the answer choices are pretty far apart here, we don't actually need the exact numbers. We can round to make the math quicker. And the specific heat of water is about 4.18 joules per gram Kelvin, but we can round to 4 for easier calculation. So we're solving for temperature change of the bath, and we can rearrange the question accordingly to isolate delta T. So on one side of the equation, we have the pipe, 10 grams times 0.9 joules per gram Kelvin times a temperature change of 5 degrees Celsius, which gives us 10 times 0.9 times 5 equals 45 joules. And then on the other side, we have the bath. So 20 grams times 4 joules per gram Kelvin times delta T, that gives us 20 times 4 equals 80. So now we're solving 45 equals 80 times delta T. And that simplifies to delta T equals 45 divided by 80 equals 0.5625. And since we rounded down earlier using 4 instead of 4.184, this estimate is going to be slightly lower than the real value, meaning that the actual answer should be just a little bit smaller. So 0.5 degrees Celsius is the closest and the best choice, and that means C is our right answer. All right, so now at this point in the passage, if you're kind of feeling like you could use a refresher on some of these terms and formulas, because there's a lot to digest here, do be sure to check out our MCAT Premium Content Hub. And there we thoroughly cover every single content area, including 600 plus practice questions to help you really apply and test your knowledge, especially on some of these topics that can get pretty dense. All right, now let's look at question 2. It reads, a surface layer of aluminum on a previously manufactured prototype appears to oxidize with the atmosphere to create a film. What is the most likely identity of this newly formed film? So right off the bat, what keywords pop out for us to underline here? Oxidize is the one that sticks out the most to me. And this is actually really good practice for cars, by the way, because they will try to confuse you with details that you don't actually need. They're just trying to kind of distract you and take away from the actual main idea of the passage. So if we want to make sure that our answer matches the subject that the question is actually asking, then that means that we want our answer choice to be the answer where a limb gets oxidized here. So let's take a look at our answer options. And as you can see, all of them are oxidized to an extent since oxygen is added. But for this question, I'm going to actually go ahead and tell you the right answer, and then I'll explain how I got there. So the correct answer for this question is C, aluminum oxide. And how I got there is when you leave aluminum out in the air, it reacts with oxygen to form an oxide layer, which is very, very stable, and that protects the metal from further corrosion. Now, this layer is made primarily of aluminum oxide, since aluminum usually has an oxidation state of +3 and oxygen -2. So 2 aluminum ions is 2 times +3 equals +6. Need to counteract 3 oxide ions, which is 3 times -2 equals -6, and that gives us a neutral compound. So we can also see that because aluminum usually has a +3 state and oxygen usually has -2, then you cross the charges and you get Al2O3. And that means that C is our correct answer here. So that one was pretty quick. And next we're going to do a deep dive to answer a thermodynamics question that really frequently appears on exams. And that is how to find the entropy of a vaporization of a working fluid. And this is a really great example of how we use the Gibbs free energy equation during a phase change. So question 3 asks us, what is the entropy change when the working fluid vaporizes? And we get 4 answer choices. A, minus 100 joules per mole Kelvin. B, minus 23 joules per mole Kelvin. C, 23 joules per mole Kelvin. And D, 100 joules per mole Kelvin. So to solve this one, we're going to start with the Gibbs free energy equation, delta G equals delta H minus T delta S. During a phase change, such as boiling, the system is at equilibrium, so delta G is just 0. So we can simplify this equation to 0 equals delta H minus T delta S. And then rearranging that, we get delta S equals delta H divided by T. So now we just need to plug in the values. And from the figure associated with the question, we're told that the enthalpy of vaporization is 31.3 kilojoules per mole, and the boiling point temperature is 329.3 Kelvin. So let's convert the enthalpy into joules first, and 31.3 kilojoules per mole becomes 31,300 joules per mole. And then we'll plug in the numbers. So delta S equals 31,300 divided by 329.3. And that gives us approximately 95.07 joules per mole Kelvin. But if we round the numbers for simplicity, say 31,300 to 30,000, and then 329.3 to just 300, the math is a lot easier. So we would have 30,000 divided by 300 equals 100 joules per mole Kelvin. And so the best estimate for entropy of vaporization is 100 joules per mole Kelvin, and that gives us our final answer, choice D. So I know that's a pretty extensive explanation. I just want to give a quick conceptual shortcut here to help you if you encounter a similar problem. So when you vaporize, molecules transition from some orderly liquid arrangement to randomness, and that means entropy increases. So we would anticipate that the value is going to be something positive. So that already can allow you to cross off any negative answers like A and B immediately, and then you have fewer to deal with when you're trying to determine the correct one. Okay, let's move on to question 4. And here we're going to be looking at a thermodynamics application question, and it asks us, under which of the following conditions would the aluminum pipe no longer function as designed? So to start out, let's consider how this thermal pipe actually operates. It uses a working fluid, in this case acetone, and it depends on the fluid's ability to vaporize and condense. So that process can only occur if the fluid is in separate liquid and gaseous phases. But the twist is that once a fluid is heated to a temperature above its critical point, those phases are actually no longer distinct. In fact, the fluid is a supercritical fluid. That is, it doesn't neatly exist either as a liquid or as a gas. So as we gathered from the figure in the problem, the critical point of acetone is 508 Kelvin, meaning that at any lower temperature, regardless of the pressure, acetone no longer behaves in a way that allows for simple vaporization and condensation. So with that in mind, let's take a look at our answer choices. Choice A has a low temperature of 250 Kelvin and low pressure, well below the critical point. So acetone is pretty safely in the liquid and gas region, and that means the pipe works just fine. Then choice B is at 300 Kelvin, still well below the 508 Kelvin limit. And acetone does its usual thing again, so the pipe functions as intended. But choice C gives us a temperature of 650 Kelvin, which is way above the critical point of 508 Kelvin. And that means the acetone is now a supercritical fluid. So there isn't a sharp interface between liquid and gas. Vaporization and condensation do not occur in the way that the system was designed to have them happen. And so if those phase changes can't happen, then the aluminum heat pipe won't be able to work correctly. So at operating conditions below the critical temperature of acetone and where the phase changes of acetone are possible, the system performs as usual, but after it crosses that threshold, it stops. So that means C is actually our correct answer here, pressure of 2 atmospheres, temperature of 650 Kelvin. All right, let's look at question 5 now. Here we're going to solve a thermodynamics question that asks, what is the total enthalpy required to vaporize 0.05 moles of the working fluid initially at 298 Kelvin? And our choices are A, 285 joules, B, 1,750 joules, C, 2,170 joules, and D, 3,250 joules. So we're told that the fluid starts at 298 Kelvin, And from the figure, we know that the boiling point of the working fluid, which is acetone, is 329.3 Kelvin. So that means we're actually going to have to perform two calculations here. First, we need to calculate how much energy is required to heat the fluid from 298 Kelvin to 329.3 Kelvin. And then we need to calculate the energy needed to vaporize it at the boiling point. So we'll start with the heating part, and we'll use the equation Q equals N times C times delta T. Q is the heat energy in joules, and N is the number of moles of the substance. C is the molar heat capacity in joules per gram Kelvin, and delta T is the change in temperature in Kelvin. So this formula is a molar version of the more familiar Q equals MC delta T. But when you're working in moles and you're given or you're using molar heat capacity, C, which has units of joules per gram Kelvin, then the formula becomes Q equals N times C times delta T, which tells us how much energy is needed to raise the temperature of N moles of a substance by a given number of kelvins or degrees Celsius, since the unit difference cancels in delta T. So N is the number of moles, which here is 0.05 moles. C is the molar heat capacity of acetone, which is 125.5 joules per mole per Kelvin. And delta T is the change in temperature, which is 329.3 Kelvin minus 298 Kelvin, or 31.3 Kelvin. And for easier math, we can probably just round that to 30 Kelvin. So now we're going to plug in the values into the equation, and we'll get Q equals 125.5 joules per mole per Kelvin times 30 Kelvin times 0.05 moles, and that equals Q equals 188.25 joules. So that's the energy needed just to raise the temperature to the boiling point. And then next, we're going to calculate the energy required to vaporize the fluid at that temperature. So we're told that the enthalpy of vaporization, delta HVAP, is 31.3 kilojoules per mole, which we convert to 31,300 joules per mole. And now we're going to multiply that by the number of moles, which is 0.05 moles. And we get Q equals 31,300 joules per mole times 0.05 moles. And that's going to equal 1,565 joules. So heating the liquid took 188.25 joules, and then vaporizing it took 1,565 joules. So we get the total enthalpy by adding them together. 188.25 joules plus 1,565 joules equals 1,753.25 joules. And the closest answer to that choice is B, 1,750 joules. So that is our answer here. Okay, we made it to the last question. So this is a fun little heat transfer problem. Question 6 asks, the transfer of heat between points T1 and T5 can be best described as occurring through A, conduction, B, induction, C, convection, or D, radiation. So work this out. Let's just unpack what each form of heat transfer amounts to and then match it to what's occurring between T1 and T5. Choice A, conduction, is heat transfer through direct contact between materials, like heat traveling along a metal rod. So it really concerns the collisions of molecules, but no fluid flow. So A is definitely wrong in this case. B, induction, is the process of heating a material with an alternating electric current, typically a metal, through a magnetic field, like with an induction cooktop or something. So that really has nothing to do with heat being transported by a fluid either, so B is also wrong. Now, option C, convection, is the transfer of heat by the movement of a fluid, a liquid, or a gas. So the working fluid is traveling through a pipe from T1 to T5, and as it does so, it's transporting a quantity of heat with it. This is really the textbook characterization of convection, heat transported due to the bulk motion of the fluid. So C looks like a good answer option, but let's go ahead and check D and confirm that that's wrong. So option D, radiation, is heat transfer through waves of electromagnetic energy like sunlight hitting your skin. It doesn't actually need a medium or any contact whatsoever. So again, that's not at all how things are happening in this problem. The fluid is moving. It's actively moving the heat from point T1 to point T5. So we can be sure now that C is the correct answer. All right, and with that, it looks like we survived to the end of the passage. That was a pretty dense one. Thanks for joining. We really hope that this walkthrough was helpful in your MCAT journey. If you're looking for more practice resources, you can visit our MCAT QBank or our Premium Content Hub for thousands of sample problems. Or if you want a more personalized approach, our MCAT experts provide one-on-one tutoring and also individualized study schedules and test-taking strategies that just go a step further than that content review. You can check out our website to learn more, or feel free to drop a comment here with any questions you might have. Otherwise, happy studying.